When studying electromagnetism, you need to know a few basic rules. First of all, you need to know the definition of electromagnetism, and that is, it's the force of attraction or repulsion of a magnet due to the arrangements of its atoms. Secondly, you need to know that magnetic field lines will always go north to south. So if we have a magnet like this, with this is the north end and this is the south, the magnetic field will be going from north to south just like this, all the way through the magnet. A third thing you need to know is that the direction of the force is always perpendicular to both the direction of I, the current, and the magnetic field. For example, if you have two wires like this, and there is a current going up and a magnetic field going to the left, the force will be coming out of the page. That means you have the current up and the force out, which creates a 90-degree angle, which is perpendicular. You also have the force going out and the magnetic field going to the left, which also makes a 90-degree angle, which is perpendicular. So the force is always perpendicular to both the current and the magnetic field, even though the current and magnetic field are not in the same direction. The fourth thing you need to know is that opposites attract and likes repel. Therefore, north and a south pole will attract each other, but a south and a south pole will repel each other. The fifth thing you need to know is that there's never just a north or south pole. So if you have a magnet with a north and south pole and you break it, it now becomes a magnet with a north and south pole each. So two south and two north on both magnets. You never have just a north pole. There are three right-hand rules to finding variables in electromagnetism. The first one you use when you're finding magnetic field. The second one you use when you're trying to find the direction of the force. And the last one, number 3, you use when you're finding which way north is. So here are some examples. This is our wire. The first one, when you're finding the magnetic field, you're going to point your thumb in the direction of the current, which is going up in this case. Curl your fingers, and that's where your magnetic field is. So in this case, my magnetic field is wrapping around the wire. For number 2, the right-hand rule, number 2, you're going to point your hand in the direction of the current, which is going up in this case. You're going to curl your fingers in the direction of the magnetic field, which is going towards the left in this case. And wherever your thumb is pointing when you stick it out, that is the direction of the force. So in this case, the direction of the force is out towards you. And it's coming towards you out of the page. That represents out of the page. This represents into page. And this one would be our force in this case. Our last one for finding north, you're going to curl your fingers in the direction of the current. So in this case, it's going to wrap around the wire like this. And your thumb shows where north is. So in this case, north would be up. And those will be your 3 right-hand rules in electromagnetism. In electromagnetism, there are many different equations we use, but the first we're going to talk about is the equation for a force on a wire, and that is F equals BIL sine theta, with F being the force measured in newtons, B being the magnetic field measured in teslas, I being the current measured in amperes, and L being the length measured in meters, and the sine theta being the angle measured in degrees. So we're going to go ahead and do an example for this one. If we have an example asking for the force on a wire that is carrying a current by the magnet. if it gives us the following variables, B equals 0.8 teslas, theta equals 60 degrees, current equals 35 amps, length equals 20 centimeters. So first thing you have to do is write your equation. F equals BIL sine theta. We're going to go ahead and draw a picture just to show us. Here's north, here's south. Here's the wire that they're talking about right here in the middle of those two. The magnetic field is going this way. And this angle right here is 60 degrees. And this picture would go with the problem. They would give us this information. So next thing you're going to do is to plug in your variables. But if you look, length is measured in centimeters, and we set up here that it has to be measured in meters. So we have to change this to 0.2 meters in order for it to calculate right. So we're looking for F. So we go ahead and plug in F equals B, which is 0.8 teslas, times I, which is 35 amps, times L, which is 0.2 meters, not 20 centimeters, and sine theta, theta being 60 degrees, because we see that in our picture over here. When you calculate that, you're going to get the force equals 4.8 newtons. And that's how you measure the force on a wire. The next equation we're going to look at is for force on a charge. And that equation is similar to force on a wire, but just a little bit different. It is F equals QVB sine theta, with F being again the force, and that is measured in newtons, with Q being the charge, and that is measured in coulombs, with V being the velocity, that's measured in meters per second, with B being again the magnetic field, and that is measured in teslas, and theta again being the angle measured in degrees. So we're going to go ahead and work out a problem for this one as well. Let's say your problem says you have a proton that moves in a magnetic field. B equals 0.5 teslas with a speed of 1 times 10 to the 7th meters per second when there's a 45-degree angle between the velocity and magnetic field, B. And this is saying that a proton has a charge of 1.6 times 10 to the 19 coulombs. So first we're going to write our equation, and that is F equals QVB sine theta. Let's write out our variables. We have Q equals 1.6 times 10 to the negative 19 coulombs. We have V equals 1 times 10 to the 7th meters per second. We have B, which equals 0.5 teslas. And we have theta, which equals 45 degrees. So we can go ahead and plug in for our equation. We're looking for F, and that equals 1.6 times 10 to the negative 19 coulombs times 1 times 10 to the 7th meters per second times 0.5 teslas times sine to the 45 degrees. And whenever you put that in your calculator, you're going to get 5.7 times 10 to the negative 13 newtons. And that is the force on the proton, on the charge.